So now we're going to talk about action potentials. We've already gone over how the dendrites receive graded potentials, and those all add temporally and spatially at the trigger zone. Then if they reach the threshold of negative 55 millivolts or greater, and that means they're going to propagate an action potential. But one thing about an action potential is that they're all equal. So the action potentials, the amplitude or the potential change, the electricity that's going to be passed, chemically speaking, is going to be the same. Now I know I'm not drawing them all equally, but just imagine they're all the same. So that's how it functions throughout the axon. Now I want to explain to you what happens specifically when an action potential does occur. So step one, our axon hillock is at negative 70. That's its resting membrane potential. Step two, some kind of depolarizing stimulus. Depolarizing is excitatory, which means that's either sodium or potassium or calcium. Sodium or calcium, positive ions. Let's say the axon hillock gets to negative 57. Nope, too bad. I gotta go back to negative 70. Let's say it gets to negative 60. Nope, too bad. I gotta get to negative 50. I didn't get to negative 55. I didn't reach the threshold, so it goes back to negative 70. So let's say this one manages to reach negative 54. So what was coming in right now? Some excitatory PSP, postsynaptic potentials, sodium, calcium. But now at negative 55, I zoom forward. I zoom all the way to negative 20. So what happened is at negative 55, I reached that threshold. All my voltage gated sodium channels, all of these channels, so I'm going to put voltage gated VG Na plus to mean voltage gated sodium channels open, lets all the sodium in that usually couldn't get in because of the membrane permeability, makes it positive. So instead of being negative, it goes all the way to positive. Right at the top, these voltage gated sodium channels, they inactivate. So I'm going to put Na plus inactivates, inactive. So it can't open no matter what. It's different from being closed. Going down, we want to return it to normal so it can fire again. So the way we're going to repolarize this cell and reach negative 70 is actually going to be through kicking out potassium. So we're going to open voltage gated potassium channels, and we're going to kick that out of the cell. That makes it negative because if we're taking out positive potassium from the cell, it's going to make it negative all the way to negative 70. That's repolarization. However, once we close these guys, they don't respond very well. So even though they're supposed to be closed at negative 70, they actually take a while to close. So potassium keeps getting kicked out, and it actually goes down to about like negative 90. So this portion where it's less than negative 70, this is called hyperpolarization. Hyperpolar. I'll just write hyperpolar, and it ends up balancing itself out, and it gets back to neutral. Once the potassium channels realize that they should close, it all ends up being chemically balanced at negative 70. And then one thing that helps me return that negative 70 resting membrane potential is the sodium potassium pump. And remember, the way it works is that it kicks out 3 of these sodiums and puts in 2 of these potassium. If I kick out 3 positives and I put in 2 positives, that's a net negative inside. It's like if I give someone $3 and I get back $2, I still am owed, or I'm in the negative $1. Hence the negative 70. And then those are the steps. So the last thing I wanted to go over is that these were the voltage gated potassium channels that repolarized. What hyperpolarized, they're still the voltage gated, but don't call them that. Call them slow potassium channels. Okay? and then that'll get you your full points.